back to the first year topic. We were studying the periodic classification of the elements and trends in the periodic properties. Among them, various properties like the atomic radii, along with ionic radii and isoelectronic species we have studied. Then we have studied electron gain enthalpy. Okay, then ionization energy. Now let us go for one more such property that is called as electro negativity. Electro negativity. When we consider this electro negativity, it is actually a comparable property, not for the individual atom. It is actually used for the comparison of the electron attracting tendencies of the different elements. So, the other three properties are absolute for the particular atom. For example, atomic radius. It is defined as the distance between the nucleus and the outermost electron, where the electron density becomes 0. Similarly, ionization energy is the energy required to remove an electron. Electron gain enthalpy is energy either required or absorbed, required or released when an electron is added to an atom. But here we consider this electronegativity as a comparable property. So when you consider an atom A attached to an atom B by a covalent bond, assume that it is a covalent bond, then one of these two elements will have the tendency to attract the electron density more towards itself. So that tendency of attracting the electron density from a covalent bond, single covalent bond, is called the electronegativity. That is, with comparison to the one atom, the other atom has got the tendency to attract the electron density. That's why such a property is named as the comparative property, that is electronegativity. So this electronegativity is defined as electronegativity is the tendency of an atom to attract electron density or to attract electron from a single covalent bond between two atoms. That is, when you consider this A and B, assume that this is the covalent bond as I told you. Covalent bond is nothing but a pair of electrons. So when this electron density is attracted by this B, then we say B is more electronegative than the A. So to measure the electronegativities, it has no unit, only the tendency to attract the electron density. That's why it has no unit. Electronegativity has no unit. For example, ionization energy, electron gain enthalpy, they are measured in terms of kilojoules per mole. But electron negativity has no unit. The second point is, it is a comparative property, comparative value. So we use different scales. The most important among the scales to measure the electronegativity is Pauling's scale. In this Pauling's scale, the highest electronegativity is for the fluorine atom. So fluorine is given the unit of 4 electronegativities. So comparing to that one, we measure the electronegativities of the different. There is an equation to calculate the electronegativities that is beyond the scope of this level. So when we consider this electronegativity, fluorine has got the maximum electronegativity. That is considered as the 4 units. Comparing to that one, the other elements have got the different electronegativity values. For example, in the second period, we have lithium, beryllium, boron, carbon, nitrogen, oxygen, then fluorine. Remember, this fluorine has got the 4 units. fluorine 4 units. Then you decrease this electronegativity 0.5 unit from right to left. So this will be having 3.5. This is having 3.0. This is having 2.5, 2.0, 1.5 and then 1. Otherwise you remember lithium is having unit of 1. So as we move from left to right, electronegativity increases. Tendency to attract the electron from a covalent bond goes on increasing. So fluorine has got the 4 unit. To remember the values in this second period, it is easy. From lithium you go on increasing for every element by 0.5 unit. Or start from the 4 and decrease by 0.5 unit when we move from right to left. But in the third period, as we move from top to bottom, electronegativity decreases. That's why this lithium, comparing to that lithium, sodium is having less. That is about 0.8. Sodium is having 0.9. Similarly, magnesium. Again, beryllium, when we move from top to bottom, it becomes magnesium, it is 1.2. Then aluminium, 1.5. For carbon, the next element is silicon. It is having 1.8. Phosphorus 2.1. Then sulfur 2.5. Chlorine 3. So as we move down the group, the electronegativity decreases. While when we move from left to right, electronegativity increases. Tendency to attract the electron density becomes more and more. Then you remember for potassium it is just 0.8. For rubidium it is 0.8. For cesium it is 0.7. Similarly, when we move down from the fluorine to the astatine, for bromine it is 2.8. For iodine it is 2.5. For astatine it is 2.2. Remember, there is one more element, that is hydrogen, which is having 2.2. Why these values are useful? When we consider this electronegativity of the different elements, when we observe the variation across the period, it goes on increasing and decreases down the group. Then by using these electronegativity values, we can compare whether the molecule is ionic or partially covalent or covalent, 100% covalent, like that. So by using this Pauling scale, by knowing the electronegativities, we can compare the strength of the bond, ionic strength of the bond, that is a covalent bond. For example, assume that this electronegativity of an element A is considered as chi A. It is chi, CHI chi. Similarly, the other element is having the electronegativity B. So chi A, chi B, you have to take the difference. Then this is the nature of bond. Nature of bond AB. When we consider this nature of the bond, that can be calculated by using the difference in the chi A, chi B. Suppose it is 0, is equal to 0. That means when we consider the same elements, like hydrogen molecule, hydrogen, they are having same electronegativity. So for such a molecule, it is 100% covalent. 100% covalent. Similarly, when you take this F2, H2, F2, Cl2, like that. So the molecule becomes non-polar, that is covalent. When the difference is less than 0.4, again it is non-polar covalent. Non-polar covalent. When the value is between 0.4 and 0.7, it is polar covalent. It is less ionic. Less ionic. When the value is more than 1.7, it is 50% ionic. When the value is equal to 1.7, chi A, chi B value is 1.7 difference, then it is 50% ionic. When it is more than 1.7, it is 100 more ionic, more than 50% ionic. So we can calculate the ionic character by considering this difference in the electronegativities. Let us take some example. To calculate the polar or non-polar nature of the bond, we have to use this electronegativities that is given by Pauling. Suppose I take this hydrogen fluoride molecule. Hydrogen is having 2.2, fluorine is having 4. So the difference between chi A, chi B is equal to 4.0 minus 2.2. It is 1.8. Since it is more than 1.7, it is more ionic. So hydrogen fluoride is an ionic molecule. Suppose you take this HCl. The difference between these two is 3.0 and 2.2. It is just 0.8. 0.8 is it is 1.7, less than 1.7. So less than 1.7 corresponds to less, it is polar, it is more ionic. For HF it is more ionic, it is polar but covalent. When you consider this hydrogen and sodium, 0.9 and 2.2, the difference is 1.3. 1.3 means it is almost more than 0.7, it is ionic. Similarly, by considering this sodium bromide, you can take sodium bromide. Sodium is having 0.9 while bromine is having 2.8. So it is, the difference is 1.9, more than 1.7, so it is ionic. So the ionic character of the covalent bond can be measured by considering the difference in the electronegativities. Okay, so that is about the topic on the electronegativities. There is one more small topic, that is diagonal relationship. Diagonal relationship. This diagonal relationship is explained by considering the various physical properties like atomic radius, electronegativity, ionization energy, etc. Now if you consider this lithium in the second period. Now you observe, second period first group contains lithium, while third period second group contains magnesium. So this is first group, this is second group. Let me write this lithium, beryllium. Then third period sodium and magnesium. Similarly beryllium, afterwards we have this 13th group element, that is boron. Then next one is aluminium. When we consider this element having present in a particular group in the second period and next group in the third period, this lithium and beryllium have got almost similar properties, because as we move down the atomic radius decreases, while as we move across atomic radius decreases. So lithium and magnesium have got similar chemical properties. For example, when we consider this lithium chloride and magnesium chloride, these are almost covalent. The bond is covalent bond. Even though magnesium is a metal, its chloride is behaving like a covalent molecule. It is because lithium and magnesium are diagonally related and their properties are almost identical. Similarly, beryllium and aluminium, they are diagonally related, therefore they have the similar chemical properties. That's why such a relationship between an element in a particular group in the second period and another element in the third period next group having similar chemical properties is called as the diagonal relationship. So we can predict the properties of the magnesium compounds comparing to lithium compounds. Okay. Similarly, the ionization energy, the electron gain enthalpy, and especially that crystal stability, we can explain by considering this diagonal relationship. There are some more topics like valency, the chemical nature of the oxides, etc., that we shall discuss in the next video. Thank you.